Hi friends, here we are in 6.2 looking at some trig equations. So I just want you to see through this section, we will be solving problems, equations that have some trig functions in them. So just for a few examples, notice I've got several trig equations, trig functions, sine and tangent. There's an equal sign and something else that it equals on the other side, right? These are all examples of some trig equations. So as we get in to solve, that's what you'll be working on. But before we do that, I just need to clarify something and how this relates to 6.1. All right, so in 6.1, we looked at inverse trig functions. That's super important to remember the difference between what we did in 6.1 and 6.2. So in 6.1, you looked at something that looked like this. And maybe it was an x, maybe it was a theta, or maybe they actually plugged in a value there and said solve for y. But notice you're given an equation that either has the inverse symbol or the arc symbol. Both of those are inverse functions. And we learned that inverse trig functions actually aren't functions unless you restrict where you're pulling the range from, right? These do not pass the vertical line test as is. So the entirety of 6.1 made you consider where you're allowed to look for these solutions. So if you remember, sine and tangent, the inverse sine and inverse tangent or arctangent, whatever you want to call them, I just want to get you used to both notations. You could only look in quadrant 1 and quadrant 4. Everything else is a repeat. And this meant that you were selecting solutions between negative pi over 2 and positive pi over 2. So the range, your y solutions for sine and tangent, ranged between negative pi over 2 and positive pi over 2. Cosine is a little different because if you have an inverse cosine function, then quadrant 1 and quadrant 4 are going to be a bunch of repeats, right? Cosine is positive in both those quadrants. You're going to get a bunch of the same answers. So for cosine, remember it was quadrant 1, and quadrant 2 is where you'd look for your negative values for quadrant 2. So my range for cosine, my restriction went from 0 to pi. And your 6.1 homework was full of questions where they would ask you things like, hey, find the inverse cosine of 1/2, right? And you'd be like, all right, well, cosine of 1/2, that's at pi over 6. But you'd have to consider what's in the right region. Pi over 6 in quadrant 1, 5 pi over 6 in quadrant 2. It's negative in quadrant 2, so my answer would be 5 pi over 6. So anytime you have problems, anytime on the test or whatever, and the question is an inverse function question, so it either has the little inverse symbol or it has the arc symbol, questions like this, like I just said, arc sine a rad 3 over 2, well, that is something I have to consider the quadrant. I know my answer is restricted. What would that be? Y would have to be pi over 3. If it's in radians, degrees, 60 degrees. And that's it. That's my only solution that I can give. 1 in radians, 1 in degrees. It's the same thing for the arc sine of rad 3 over 2. Because it is an inverse trig function. So know that restrictions apply only to my inverse trig functions. Something that looks like this or any of those above. Today you're going to have equations that look like this. That is not an inverse trig function, and therefore my restriction does not apply. I am going to give all solutions that will work for that. So you've kind of done this before, although you might not have thought about it in this way. Let's go back. Maybe this will help make sense between the difference between these two things. If you were just given, I don't know, way back when, right? If you were just given this problem on a page and asked to solve, you would say, oh, well, the square root of 49 is 7. 7 only. It's assumed to just be positive because they didn't put plus or minus out front. You're just doing the operation that's the page. We only give that value. If I asked you what the negative square root of 25 is, then you'd say -5, right? You write exactly what the answer is to the given problem. But if you were solving something like x squared equals 49, and now you square root both sides, you take the inverse function on both sides, well, now my answer has to be plus or minus 7, because I do have to consider all possibilities when I am the one who square roots, who takes the inverse function of both sides. The same is true with today's information. That's just sort of a little glimpse of the difference between those two sections. Let's kind of go back and do a few algebra equations before we jump into the trig equations. So I've just given you a couple algebra review questions at the top there. Number 1, you're solving for x squared. So the inverse, the opposite operation of subtracting 8 would be adding 8 to both sides. The opposite of multiplying by 2 would be dividing by 2. And I'd end up with this x squared equals 4. And I square root both sides, and I get plus or minus 2 for my solution. Both of those answers, those are the only two things in the entire universe that if I plug them back into the original equation, will give me 0 on the right side. Example 2 is also a polynomial, but this time I don't have the option of just isolating the x. I have two different sort of values of x. I've got x squared and x, so this is one I would have to factor. Luckily, we've been doing some practice factoring. So I know that would be x and x, and two things that multiply to give me -6 and add to give me -5. I'll let you think about that for a minute. It would have to be -6 and a +1. And I would guess some of you put 2 and 3 in there. -2 and a -3 would add to give me -5, but it wouldn't multiply to give me -6. And if you change the signs, then it's no longer going to add to give me -5. So just be careful on that one. Now to solve when I have these two binomials, I know if a times b equals 0, then either a or b must equal 0. So a is x minus 6, that either has to equal 0 or x plus 1 has to equal 0. So I add 6, x would equal +6 on this guy, and x equals -1. And I'd get two solutions. Both of those would work if I plugged them into the left side, and my value for x, I would get 0 on the right side. So just a quick algebra review, because some of those properties we will definitely use in these trig functions. And then number 3, I'm solving, being asked where does the sine of theta equal 1/2. I'm going to inverse sine both sides, or arc sine, and I'm going to end up with arc sine of 1/2. And I have to stop and consider, well, where does the sine equal 1/2? And so you might grab your unit circle. If you are good at the hand trick, I've got to make the bottom finger a 1. So I'm looking at the slowest angle of 30 degrees. Sine equals 1/2 there. But it also equals 1/2. Well, quadrant 2 sine is positive as well. So that same reference angle of 30 degrees would be 150 degrees. So it equals 1/2 there as well. And every possible coterminal angle to both of those. I don't have to worry about quadrant 3 and quadrant 4. Since this is a positive 1/2, those won't be options. But every time I hit possible answers for theta would be 30 degrees, 150 degrees. And of course I could answer in radians as well. Going back around again, well, 360 plus 30 would be 390 degrees. And if I go all the way back over to 150, I hit that one right there, 150 plus 360. Oh, I'm extending my, is that 510? I think. 360, 11, yeah, 510. And I could keep going, like indefinitely, continuing to add 360 every time. So you can see that answering these questions could be potentially tedious. So there's a couple things you need to know when solving trig equations. They're not all terrible. A lot of times they're pretty straightforward and easy, but you will have to pay attention to, first of all, whether is it degrees or radians. Right, that's going to change how you answer, if you're going to answer in degrees versus radians. And then they'll also have to tell you if they want all solutions, all possible in the known universe, versus an interval. And they might just tell you like a range to look in. So let me show you what both of those look like. Same equation that we're going to solve in A and in B. Notice the difference. I'm solving 2 times the sine of theta plus 1 equals 0 in both of these. Here, they're telling me an interval to look in. I only want answers between 0 and 360 degrees. And in that one problem, they've told me it's obviously degrees. If they wanted it in radians, they would have said 0 to 2 pi, and they didn't. So I'm definitely in degrees, and I'm definitely looking at an interval. So I'm only going to have 2 solutions listed in that interval. If it's all, then I would have an infinite number of solutions, and I'll show you how to respond to that. So let's go through and solve the equation, and we'll worry about our answer in a minute. I've got to rewrite it, just a habit. So I'm going to solve, subtract 1, divide by 2. I'll take all the little steps just in case somebody's, algebra is weak. So I'm solving the equation. What does the sine of theta equal? Negative 1/2. So that means the inverse sine of negative 1/2. And I would grab, since I'm only looking from 0 to 360, and honestly, I'd grab my unit circle anyway, or at least consider. I'm not actually using one. I can kind of picture it in my head. Sine of theta equals 1/2 again. We did this just a second ago, right? This would be the point root 3 over 2, comma 1/2. And this is the point negative root 3 over 2, comma 1/2. And since we're talking about sine, right, and it's cosine sine in the parentheses, then both of these positions have a sine of 1/2. So I just need to identify what those two positions are. On my unit circle, it's the 30-degree angle and the 150-degree angle. And that would be it. Those are the only two solutions for where sine can equal 1/2 as I glance one time around that circle. That's from 0 to 360. Those are the only 2 times I hit 1/2. Now, if it was a bigger interval or I had to wrap around more, then I would hit them again. I would get another answer right here and another answer right here every time I wrap around. But that's that for that one. Now, notice the second one says find all solutions. Not just the solutions in that one interval, but all solutions ever. That means wrapping around negative, wrapping around multiple times. What are all the possible solutions? So here's how you do that. I would still, it's always easiest for me, is if I want at least a glimpse of one time around the circle. So if I'm doing all solutions, I'm going to do the same thing I did up here. I'm still going to sort of give myself a picture. And I would highly recommend giving yourself a picture. I suppose if you're looking at your unit circle, that is your picture. But I would say typically when I'm grading these on my grading these tests, the students that miss them have no picture. People who draw a picture tend to get them right. So just a hint for whatever that's worth. So if I want all solutions, I know that at 30 degrees here, and every time I wrap around, every coterminal angle, remember coterminal angles, you're going to add 360 however many times you wrap around the circle. So I can use this equation, 30 degrees plus 360n, where n is the number of times I've wrapped around the circle. So if n is 0, right, then I just get 30 degrees. If n equals 1, then I get 30 plus 360, which is where that 390 comes from. If n equals 2, then I'm going to get the next one. I'm not even sure what it is, 750 maybe. And n can be negative as well. If n equals -1, then I get my first negative angle of -330, and so on. So anytime you're asked to find all solutions, keep in mind that's where you're just going to find a formula to represent all solutions. Now that only represents every time I am at 30 degrees. And I need another equation for every time I'm at the second position of 150 degrees. So I'd put 150 plus 360n. Now I kept it degrees because the last one was degrees, but keep in mind, if they asked me for radians instead, it would look the same, except for I would just have pi over 6 and 5 pi over 6 for my 2 solutions in that range, and then pi over 6 plus 2 pi n, and 5 pi over 6 plus 2 pi n. Remember, 2 pi and 360, same thing, one trip around the circle. So that's basically it. So you probably, you've gotten all the new information. You're going to solve trig functions just like you solve algebraic equations or functions. And then you just have to pay attention to how you want your answer, since, again, there can be potentially an infinite number of answers, or they might want it in range, degrees, or radians. So there's lots of things to pay attention to. The rest is just additional practice. So I'm not saying you should quit and go do it. You do want this practice because you've probably never done some of this stuff or looked at it this way. So hang in there. The next example, example 2, is an example where you're going to solve by factoring. So I've got sine theta tangent theta equals sine theta. Now, some people might quickly say, why do I have to solve by factoring? Let's just divide by sine theta, right? I'm sure I will have someone in this class that's like, hey, sine theta divided by sine theta gets rid of that, and you just have tangent of theta equals 1, and you'd solve from there. There's always going to be a problem. If you don't remember this from algebra, you never want to divide out a variable. And sine of theta is a variable, so it's going to cause you some problems if you do that. You cannot divide that out. So let's work through this. If I factored, anytime your instinct is to divide, that's a big, big hint that you probably want to factor instead. So I'm going to move that sign over, just like you would if you were actually factoring. You move that sign over in an algebra equation, and then I'm going to factor out the sign. Factoring is a form of division. It just doesn't divide across the equal sign, right? I essentially am pulling out the sine of theta and dividing both terms by sine of theta and pulling that out front. So that's what I get. Now I have the a times b equals 0, right? A is my sine of theta, and b is my tangent of theta minus 1. So I've got two different things that equal. One of them has to be equal to 0. So sine of theta maybe equals 0 as one option, or tangent of theta minus 1. If either of these instances happen, you have a solution to your function. So let's solve sine of theta first. And again, I'm either grabbing a completed unit circle or considering where on the unit circle does the sine of theta equal 0. Well, I know it equals 0 here at 0 degrees. And again, they did ask me for degrees, so that'll work. And then I know it also equals 0 on at 180. So if I'm just looking at an interval, I don't need all of them. It just says find in this interval from here to here where sine equals 0. Well, I just found them. One is right here at 0 degrees and the other is at 180. So I would say 0 and 180. Those are two solutions. If I plug in 0 or 180, and for theta up here in this original equation, I would get it equals 0. My other equation, though, gives me two additional answers. If I add 1 to both sides, remember you're always trying to isolate the variable, and I inverse tangent, I guess that's the same thing I did over here, inverse sine, and I didn't write it out. I am looking for the inverse tangent, or where does the tangent of theta equal 1? So tangent equals 1 at 45 degrees in all quadrants. It's just negative in some, right? So this is quadrant 1, tangent would be positive. Quadrant 2 at 45 degrees would also be a solution, but it would be negative, and I'm looking for a positive one. The other place where the tangent is 1 is down here in quadrant 3 at the 45-degree angle here. If you remember, 180 plus 45 is 225. So my two solutions would be 45 and 225. So within just one trip around the circle, 0 to 360, I get these four answers. 0 degrees and 180 for the sine function, and 45 and 225 from the tangent function. All of those, when I plug those in for theta, would give me 0. So back to the original strategy of potentially just dividing out. If your thought was, hey, let's just divide off sine, and the sine ended up disappearing, you would have only have gotten half the answers, right? You would have gotten just these two. You would have said 45 and 225 are your solutions, and you would have missed these two solutions just because sine disappeared when you solved it that way. So don't divide. That's what this caution is here. Don't divide by anything with a theta or a variable in it. Never divide by a variable expression. You will miss some of your solutions. All right, try B. Pause the video, try B. Notice this time your answer is still in an interval, but what's different? They want radians. All right, hopefully you pause the video. If not, do it still. Here's a chance before I start doing it. I see that each side has a cosine theta, so I'm going to subtract the other one over, make it equal 0, factor out a cosine theta, and I'm left with 2 sine squared minus 1 equals 0. So I've got A times B equals 0, which means either A is 0 or B is 0 or both. So cosine of theta has to either equal 0 and 2 sine squared of theta minus 1 if that equals 0. In either case, you're going to get 0 for a solution. So I'll solve the first one. Where does the cosine equal 0? The inverse cosine of 0. I know it's got to be on an axis, but remember it's not here. Cosine is equal to 1 and negative 1. I'm looking at the top and bottom, my y-axis values, right? This is where the cosine equals 0 and that. So 90 and 270, except for, remember, I want radians. So theta for this first one would be pi over 2 and 3 pi over 2. And then I have a little more solving to do on this. I'm going to add 1 to the other side, divide by 2, and then square root both sides, which would give me the sine of theta equals plus or minus, because I took the square root of both sides, the square root of 1 is 1, the square root of 2 is 2. Be careful, a lot of people look at that and just say 1/2. That isn't 1/2 because you're going to have to square root it. By the time I'm done here rationalizing, I am looking for where the sine of theta is either plus or minus root 2 over 2. So that's everywhere that sine is root 2 over 2, positive or negative. That means there's going to be an answer in all 4 quadrants. And if you remember, sine is root 2 over 2 at 45 degrees or pi over 4. And since it can be positive or negative, I'm pulling all 4. Oops, that was supposed to be straight. I'm pulling all 4 pi over 4 angles for my answer. So all 4 of these guys, all the pi over 4 angles in one time around the circle. So 1 pi over 4, 3 pi over 4, 5 pi over 4, and it's not 6 pi over 4, 7 pi over 4. So I've got 6 solutions this time, plugging in pi over 2, 3 pi over 2, pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4 all would work in this equation. You can try it, and you'll see that they equal 0 when you do that. All right, so we're going to do a couple now where we're solving this time by factoring, which we've been doing, although the factoring problem's a little different. And I want all exact solutions. So when you get that, that means you're going to write the plus 2 pi n or plus 360 n, depending on if you're in degrees or radians. It does say degrees, so just remember, I'm going to give myself a little note, plus 360 n is going to go on the end of any solution I get. All right, I see I have a binomial, not a binomial, excuse me, a quadratic. I've got a cosine squared and a cosine that's not squared. So I'm guessing I'm factoring this like I would a normal trinomial. Unfortunately, I do see there's a 2 in front. I know lots of people don't like to factor that way. Minus 1 equals 0. So this is what I'm trying to factor. And again, if the cosines bother you, ignore them. Essentially, I'm factoring that quadratic. So use your method of choice. If you like bottoms up, use bottoms up. There's nothing wrong with that. I'm just like guess and check better. This one's pretty easy. 2x can only be 2x and x. 2x squared can only be 2x and x. And 1 can only be 1 and 1. So I just need to figure out the signs. I need the middle term to add to negative x. This is 1x. This is 2x. And if I want it to be a negative x, that means this should be negative and that should be positive. So I'm going to put a plus here and a minus there. You're always checking the inside and the outside foiling to find the middle term. So I'm going to go ahead and erase that a little bit so I can have some space. So I know this is 2 cosine x minus 1 times cosine x minus 1, whoops, equals 0. So again, I have a times b equals 0. So a or b, either one of them, if they equal 0, they give us a solution. So 2 cosine x minus 1 could equal 0, or cosine x minus 1 equals 0. I'll solve both of those equations. Subtract 1, divide by 2. I'm sorry, add 1, divide by 2. And so I'm looking for where the cosine x equals 1/2. I'm going to go ahead and solve this one at the same time. All I have to do is add 1 over. So those are my two solutions. Where does the cosine of x, what's the x value, the angle value that would give me a cosine of 1/2? So I'm going to think through my unit circle, or maybe you've grabbed one and you're looking at where does the x value, right? In cosine, it's x, y. This is your cosine. You're looking for where does it equal positive 1/2. And it does equal positive in both quadrant 1 and 4, right? All students take calculus. So cosine is positive in 1 and 4. Cosine is 1/2 up here at 60 degrees, since it said I wanted to. So it's 60 degrees plus 360n. Right? It's going to, there, and every coterminal angle with 60 degrees. And then also in quadrant 4, the 60-degree angle in quadrant 4, this is 330, nope, 300, sorry. I can do math, but I only want to erase that. There we go. 300 degrees is 60 degrees south of 330. So my other solution would be 300 plus every coterminal angle with 300 degrees. So those two equations give me all possible solutions for that first equation. And then I'm considering where does the cosine of x equal positive 1? Well, positive 1, that's here at 0. Now you might be saying, well, what about 360? Well, yes, it does at 360 as well, but the smallest value in degrees would be 0 degrees plus 360n. And I don't have to put 0 plus 360. That's sort of silly. I would just put 360n if I'm writing an equation. So I get 3 equations. And maybe you're wondering, because so far there's always been 2 possible answers, and maybe you're like, well, what about this guy? Doesn't cosine equal 1 there also? And no, it doesn't, right? It equals -1. 1 and -1 are the only numbers that don't have a partner somewhere else on this equation. I mean, on this circle, right? 1/2, there's 2 1/2s. In the x position, there's 2 square root of 3 over 2s. There's 2 negative square root of 3. Everything comes in pairs except for 1 and -1. So I only have one solution for positive 1 in one trip around the circle, and then I consider all coterminal angles with that angle. Sorry, lost my train of thought. All right. I know it's a lot of stuff, a lot of algebra to review, and then if you don't know your unit circle well, you're sort of in trouble at this point. But we have been warning you. You can't say we haven't warned you about the unit circle over and over and over again. So, yeah. Okay, next equation, it looks quadratic like the last one, except for notice they're two different trig functions. So if that happens, if you end up with a problem that has two different trig functions, you're probably going to use an identity. I mean, I suppose there are some, like we had up here, that had two different trig functions, right? This had sines and cosines, but we were able to separate them by factoring. This one, I can't separate those. There's nothing to factor apart where I'm going to end up with the individual trig functions in different factors. That's not really an option. So it does sort of look like a binomial, but with two different trig functions, I'm probably using an identity to turn one into the other. And if you notice, you've got cotangent and cosecant, which are both related to I caught a crazy scary cat, right? Those are related. So I can use, now I can't replace this guy because he's not squared, but I can replace cotangent squared, right? If I solve this, if I rearrange this, I'm going to end up with cotangent squared, move that 1 over to the other side. I know that those two things are equal. So I can replace cotangent squared theta with cosecant squared minus 1. And then I just bring down the rest of the equation. Now I can see that that is quadratic. That's all cosecants. Let's rearrange it so I get, in descending order, cosecant squared minus 4 cosecant theta. And then if I move this 5 over, right, it's going to be plus 5. And a plus 5 and a minus 1. Plus 5 and minus 1 would be 4. I had to think a little hard about that for a minute. So I have this equation, and I don't know why I have x's and thetas. Sorry about that. This should not be different variables. They're supposed to be the same, right? That's supposed to be theta and theta. Or you could put x and x if you prefer. But now I'm trying to factor, essentially, x squared minus 4x minus 4. That's what you're factoring. If you want to drop the cosecants, if you want to change theta to x, feel free. That's the format of that function. I need two things that multiply to give me 4 and add to give me negative 4. Uh-oh. That's not going to work. Do I have a typo or did I write something down wrong? Plus 5. Oh, this should be positive 4. I did write it down wrong. All right. Didn't add right, I guess. So there's supposed to be plus, which now that works, right? Those multiply to give me positive 4 and add to give me negative 4. And they're actually the same, so that's kind of nice. I have got a times b equals 0 here. I suppose I can come back and plug this in. It's not x, it's cosecant theta minus 2 twice. So if you want, you can write them, repeat them if you want, but they are the same. They do equal 0. Square rooting both sides to get rid of the squared would leave me with a single cosecant theta minus 2 equals 0. I only have to solve one of them. I suppose if you really want to, you could solve them twice, but you're just going to get the same answer. So I'm looking for where the cosecant of theta equals positive 2. Now, unless you're really good with reciprocal functions, maybe you see it. If you don't see it, I will always change my reciprocal function into its reciprocal, and that would be 1/2. So now it's a little bit more clear. I'm looking for all exact solutions, so I'm writing in radians, that means plus 2 pi n to the end of whatever my answers are. But I still need to look in one trip around the circle so I make sure I get all of them. It's not quite straight, and that's going to bug me. There we go. So sine of theta equals 1/2. Again, we've been here before at, it's 30 degrees or pi over 6 in radians for quadrant 1. Is there anywhere else that sine of theta is positive 1/2? And hopefully remember, yep, over here in quadrant 2, it would be 5 pi over 6. So I would write my two solutions. It's pi over 6 plus 2 pi n and 5 pi over 6 plus 2 pi n. Those are my two solutions, and that's it. So to sum up sort of what your steps are when you're solving a trig equation, First of all, you're going to want to decide, is it linear or quadratic in form? So you know if you're going to factor or not. If it's linear, just solve for the variable, right? Linear means there's no power above 1, and quadratic would be squared. I suppose you could see cubics and other things in here as well. I doubt we get too crazy, but that will help if you start noticing whether it's linear or quadratic. If only one trig function is present, it's just sine, it's just cosine, then just solve the equation for that function. Pretty basic. If you've got more than one trig function present, like sines and cosines, rearrange it so that the equation equals 0, like we did in those first couple, and then try to factor so that the factors end up with just a single trig function in it. If it's a quadratic in form but not factorable, you can use the quadratic formula. That would still apply. If you're using the quadratic formula, if it's not factorable, that probably means they're not unit circle angles, and you would need a calculator to finish solving. We'll do one of those maybe on another day. And then the last thing is you can always use identities to change the form of the equation. It could be helpful to square both sides of the equation. And if you do that, make square root both sides of the equation, make sure you check for extraneous solutions. I said square root, I meant square. Okay, so let's look at a few other practice problems. If we were in class, I'd have you kind of work on these together, but obviously if you're watching this, you weren't. So let's look at this next one. I want to solve. I see that there are two different trig functions. This is an identity or a formula from last chapter. You may or may not recognize. You're not going to really want it anyway, but just for funsies, that is the cosine of 2 theta. So you could rewrite this as the cosine of 2 theta equals 0, but you don't know the rules for solving when you have multiple angles, multiples of theta. That's actually what 6.2 is all about, so let's rewind and not worry about that for now. So if you remember, I guess I could factor that even too, right? It is factorable. That's the difference of 2 squares. So I could have cosine minus sine, cosine plus sine, but now I'm sort of stuck. If I set them each equal to 0, that doesn't really help me. I have 2 different variables, and I mean, I guess technically my variable is just theta, but I have 2 different trig functions, and I can't solve that quite so easily. So the other option, remember, is always choose identities. I've got cosines and sines, and I don't want both of them, so let's just get rid of sine. Remember, sine squared is 1 minus cosine squared. That comes from this first Pythagorean identity where I've just subtracted cosine from both sides. So that gives me cosine squared theta minus 1 minus cosine squared theta equaling to 0. Be careful that you distribute, yellow's not going to work, the negative sign to both terms, so you get cosine squared theta minus 1 plus cosine squared theta. 1 cosine squared theta plus another cosine squared would be 2 cosine squared thetas. Now I only have a single value of cosine squared. If I add 1 and divide by 2, I'm going to get 1/2. I'm going to square root both sides, and I get the cosine of theta is plus or minus the square root of 1/2. Be careful, the square root of 1/2 is not the same as 1/2. You're going to get plus or minus 1 over root 2, or in other words, root 2 over 2 after you rationalize. So I'm looking for positive and negative angles where cosine is the root 2 over 2. That's going to happen in all 4 quadrants, right? At pi over 4, 3 pi over 4, oh, I want degrees. 5 pi over 4 and 7 pi over 4, but in degrees, dummy. I'm talking to myself, not you. So 45 degrees in each quadrant. 45 degrees in the second quadrant was at 135, 225, and 315. Those are my 3 answers. It's the only 3 places that you're going to get that in one trip between 0 and 360. You're going to get 4 right there, right there, right there, and right there. So those 4 answers. I do not put plus, I said, oh my goodness. Okay. I don't put plus 360n because I'm just listing out those 4 solutions are the 4 solutions for this equation in that interval. All right, I've got tangent minus cotangent equals 0. There's a couple of ways you could maybe look at this one. Can't decide what's the best here. So maybe you play with it first and see what you come up with. Here's my suggestion. I know it's tangent and cotangent, and so theoretically I'm not really able to factor. I'm playing in my head with some ideas. I know cotangent, though, is 1 over tangent. So I can technically factor out either of them. And again, I'm in my head trying to decide what's going to be easier to explain. So I can factor out a tangent out of both of these. I mean, think about this, right? This would be the tangent of theta minus 1 over the tangent of theta. So both of those do have a tangent of theta in them. So I can factor that out. Or you could factor a cotangent out, whichever you think is going to make more sense to you. So how about, I'm going to factor out a cotangent. Now remember, when you factor, that means you're dividing by that term, but you're not dividing it out, you're like dividing it and pulling it out front. So I've got tangent over cotangent. Tangent over cotangent is just going to be tangent squared, right? Because cotangent up in the numerator is another tangent. And I'm going to end up with tangent squared. And then minus, well, cotangent divided by cotangent would just be 1. So that's one way you could go about factoring and separating the 2 different trig functions you have. If you want to play with it and leave them as fractions, you could do that as well. But now, again, I've got a times b equals 0. So either cotangent of theta equals 0, and all the solutions that come from that, or tangent squared theta minus 1 equals 0. So I've got 2 equations to solve. Cotangent of theta, where does it equal 0? Well, as a tangent, that'd be 1 over 0 or undefined. I'm looking for where's the tangent undefined. So hopefully you remember the tangent is always undefined on the y-axis. So straight up, straight down, I'm in degrees, so 90 degrees and 270 would be the solution I'd get for the first one. The second one, I'm going to add 1 to both sides and square root. So I'm looking for where does the tangent of theta equal plus or minus 1? Well, tangent of theta is 1 at 45 degrees, and since I want all 4, right, it's going to be positive, negative, positive, negative. I want all 4 of them. It's all, again, all 4. Giving you a lot of degree ones. I wish I would have made more of them radians. 45, 135, 225, and 315. All right, now that's just one way I went about doing it. Remember, pretty much anything, as long as it's legal, as long as what you're doing is true, you know, any of those would, there's other options is what I'm trying to say. Sorry, I'm starting to wander. This is getting long. So any of those are going to work. And again, there's other possible ways to solve something like that. that you can try. If you get the same answer, then it works. If you don't, then it didn't work. So bring things to class if you want to ask me about different solutions. All right, one last problem that, again, is having you practice finding all exact solutions. I'm going to change this to be in radians. For crying out loud, how many degree problems do I have? All right, so I've got 3 times the cosecant x minus 2 root 3, and perhaps you're panicking because you're like, oh no, cosecant. That's okay. The good news is there's only one trig function. This is it. That is all. I just need to isolate that piece. So I'm going to add 2 root 3 to both sides. I'll do this one a little slower, right? Add 2 root 3 to both sides. That gets, at least now I don't have a binomial on the left anymore. And then I'm going to divide by 3. And I get the cosecant of x equals 2 root 3 over 3, which you might be like, what? Where in the world is that on the unit circle? Well, let's look at its reciprocal. It's going to be 3 over 2 root 3. So I'm looking for where does the sign equal that? And you may or may not recognize it because I would need to rationalize. I'd get 3 root 3 over 6. This is root 3 over 2. I'm looking for where does the sign equal root 3 over 2? Well, sine is going to equal root 3 over 2, positive root 3 over 2 in quadrant 1, and in quadrant 2 up here at pi over 3, and up here at 2 pi over 3 in radians. If you left it in degrees, it would be 60 and 120. So my two solutions for x is pi over 3 plus all coterminal angles, so 2 pi n. And then the other possible solution would be 2 pi over 3 plus 2 pi n. All right, I think that's the end. There ain't no more. So that should be enough, hopefully, for you to get in and get started on that assignment. Don't forget, bring me questions if you come across things you're not sure how to handle. We can talk about those at the beginning of class. All right, guys, good luck.